concept of work, energy, and power. Learning outcomes. By the end of this section, you should be able to define work, energy, and power, state the principle of conservation of energy, differentiate between kinetic and potential energy, derive the equations for kinetic and potential energy. 1. Concept of energy. Work is said to be done whenever a force moves a body or an object through a distance in the direction of the force, and that work is given as the product of the force and the distance moved by that force. There are various examples of work done. An example is when you drag a crate of soft drink through a distance, or when a car moves a certain distance, or when a boy climbs a staircase, and so many of them. Now, if a man is standing and carrying a heavy block of wood or concrete on his head, the man cannot be said to be doing work because he is not moving. For an object to be said to do work, it has to move through a distance by applying a force. So if a man lifts a block from the floor to his head, then the block has done a work by moving from the floor to a vertical height. So work can only be said to be done when an object moves. The concept of work is different from the ordinary day work when you say you go to your workplace to go and work. So in physics, when you talk about work, you have to talk about the movement of an object. You have to talk about the movement of an object from one place to another by the application of force. So work can only be said to be done when a force moves an object through a distance, and that object must move in the direction of the force. So we can say that work done is equal to force times distance in the direction of the force. Now if we use symbols for work, force, and distance, then the symbol for work is W, the symbol for force is F, and the symbol for distance is S. So we can say W equals F times S, which is force times distance. Now, the force must be parallel to the direction of the distance. Now, if the force is not parallel, if the force is applied at an angle an angle theta to the horizontal, then the force can be the work done can be given as, or is given as, work done is equal to force times distance times the cosine of the angle it makes with the horizontal. You can see that from the diagram below. The SI unit of work is the joule. The symbol for joule is capital letter J. So we can define the joule as the work done when a force of 1 Newton moves a distance of 1 meter. That is the definition of the joule. We have other multiple units or larger units of the joule. They are the kilojoule and the megajoule. And 1 kilojoule equals 10 raised to power 3 joules. That is 1 kilojoule is equal to 1000 joule, and 1 megajoule equals 1 million joule. So the symbol for kilojoule is kg, and the symbol for megajoules is mg. 2. Concept of energy. Energy can be defined as the ability or the capability or the capacity to do work. So energy gives you the impetus to do work. The unit of energy is the same as that of work. That is, the SI unit of energy is also what? Joule, just as we explained in the previous session with work. Energy can come in different form. So see, energy can appear in any form. Now let 3, we look at work done in a force field. Work can be done in a gravitational field. And that work done in a gravitational field is known as the weight of the object. And it is defined, or it is the force that pulls a body towards the center of the world, Earth. So the weight of a body is the force of attraction on a body as a result of the Earth's gravity acting on it. The magnitude of the work done is given by the work is equal to force times distance. Now, since the force is the weight of the object under the action of the Earth's pull or gravity on it, then we know from Newton's law of motion that force is equal to mass times acceleration, but this time around the acceleration is the acceleration due to gravity. So the work done is equals to mass times acceleration due to gravity times the height in which the object falls from or which it rises to. So the work done in a force field under a gravitational field is W, which is work done, is equal to mgh. We can define the parameters where m is the mass of the body in kilogram, g is acceleration due to gravity g, and the value is approximately equal to 10 meters per second square. H is the height in which the object rises or falls from in meters, and W is equal to work done given in what? Joules. 4. Mechanical energy. Now we have two kinds of mechanical energy. They are kinetic and potential energy. Kinetic energy is the energy a body possesses because of the virtue of its motion. An object that is in motion, an object that is moving, possesses kinetic energy. And we give the symbol for kinetic energy as E sub k, E sub k. Kinetic energy, like I said earlier, is the energy of an object due to motion. Examples of kinetic energy include, but not limited to these examples: 1. A rolling ball. 2. An object falling under gravity. 3. Wind or air in motion. 4. An athlete running a race. 5. A bullet moving. 6. A plane flying, etc., etc., and so on and so forth. We have very numerous examples. A bird that is flying in air possesses kinetic energy. So an object that is moving possesses kinetic energy. Now the work done, we want to look at how to derive the formula for kinetic energy. The work done in bringing a body that is moving with an initial velocity of v to rest. Now when an object is brought to rest, the velocity becomes 0, or the speed becomes 0. So that work done in bringing that object that is moving with a velocity to rest is equal to the kinetic energy of the body when the speed is v. Now we know that work done is equal to force times distance. So work done is equal to F times S. But we know that distance is equal to average speed times time. That is, distance is s equals half into v plus 0 times t. Remember that the initial speed was v and the final speed was 0 because the object was brought to rest. So if you work that out, v plus 0 is v, then the average distance is half vt. The average distance covered from moving an object, or from bringing an object moving with a velocity v to rest, is x equals half vt. Now force is equal to mass times acceleration. So we say that F is equal to ma, and also we know that a, acceleration, is equal to velocity over time. So therefore, from Newton's second law of motion, we know that F is also equal to change in momentum over time. So F is equal to mv over t. So if we substitute these formulas for average distance and force into the previous equation, here we said that work is equal to force times distance, then we are going to get work done equals half vt, which is the distance, times mv over t, which is the force. Now the t will cancel out each other, so we are left with the work done is equal to what? Half mv squared. Remember that we said that the work done is equal to the kinetic energy of the object. The work done in bringing the object to rest is equal to the kinetic energy when the object was moving with an initial velocity of v. So the kinetic energy equals half mv squared. Now we know that m is the mass of the object in kilogram, v is the speed in meters per second. So we say that the work done is equal to change in kinetic energy of the body. Potential energy. Potential energy is the energy of a body because of its position, or it is the energy possessed by a body because of its position. The symbol for potential energy is E sub P, E subscript P. The potential energy is also equal to work done. So it means that potential energy E sub P is equal to force times distance. And the force here is the weight of the object acting under the influence of what? Gravity. So the potential energy is mgh. The law of conservation of mechanical energy. The law of conservation of mechanical energy states that energy can be transformed from one form to another, but the total energy of the system remains the same. That is, the total energy is conserved, or we say that the sum of all the energies must remain what? Constant. So potential energy can be transformed to kinetic energy, and kinetic energy can be also transformed to potential energy, but in all the cases the sum of the energies must remain what? Constant, must be conserved. Now if we say that the kinetic energy is ek and the potential energy is E sub p, then E sub k plus E sub p, that is the kinetic energy plus the potential energy, must be constant, is equal to constant. Or we say that the sum of the potential energy and the kinetic energy at any point is equal to the sum of the kinetic energy and the potential energy at another point. Typical examples of alternating potential and kinetic energy are those of simple pendulum, the motion of a loaded spring, and an object falling from a height, or an object that is thrown up. At each point of those motion, we have the sum of the kinetic and potential energy always what? Constant. Now you should take note of this, that At the furthest point of any motion where we have alternative potential and kinetic energy, at the furthest point the potential energy is maximum. Then at the rest position, the lowest point, which is the equilibrium position, the kinetic energy is maximum. Now, at the maximum kinetic energy, the maximum velocity is equal to the square root of 2gh. That is the square root of 2 times acceleration due to gravity times the height at that point. Now, this image that you have here illustrates the energy of simple pendulum. At the two extreme ends or highest point, A and C, the total energy there is the potential energy. The kinetic energy there is 0. That is why you have the velocity at those points A and C equals 0. But the acceleration is maximum there. Now at point D and E, which is a height h above the level point of the bulb, the total energy at those points, that is at point D and E, is equal to the sum of the potential and the kinetic energy. Then at the mean position, the equilibrium position, the rest position, point B, the velocity is maximum, the kinetic energy is maximum, and the potential energy is equal to what? 0. Now this is the energy diagrams for a spring. If you look at the first diagram at the extreme left rather, the mean position is at the point where S is equal to 0. The object is stretched, that is, I'm looking at object diagram A. The object is stretched through a distance S equals A. And that distance is equal to the maximum distance the object M can move. So that is the amplitude. So the maximum energy there, or the total energy there, is the potential elastic energy, and that is giving us half k a squared. At that point, the velocity is 0. Then if you look at point B, the object M, the mass M, is at the mean position where x is equal to 0. The potential energy there is equal to 0, while the total energy is equal to the kinetic energy, which is half mv mass squared. Now at diagram C, the object is compressed to the maximum displacement from the mean position S. So it is compressed to the amplitude. The energy there, the total energy there, is the potential energy, which is half k a squared, and the kinetic energy at that point is equal to 0. If you look at object D, the object is also the mass is also at the main position. The total energy there is the kinetic energy, while the potential energy is equal to 0. Object E, the object is also stretched to a maximum position of A. So the total energy there is the elastic potential energy. In all of this, what it means that at the extreme end of the motion, the total energy is the potential energy, while at the mean position or equilibrium position, the total energy is the kinetic energy. But at any point in between the extreme end and the center of motion, the total energy is the sum of the kinetic energy and the elastic potential energy at that point. 6. We look at power. Power is defined as the time rate of doing work or the rate of transfer of energy. The average power P is equal to work done or energy expanded divided by time taken. So we can say that P equals to energy or work per second. P equals W over T. W is work and T is time. And we know that work done is force times distance. So we can say that power equals force times distance over time. Sometimes your power can be measured in horsepower. 1 horsepower is equal to 746 watts. It's approximately equal to 746 watts or 3 over 4 or 0.75 kilowatts. Now the unit of power is the watt or joules per second. So from the above equation, here we said that P is equal to force times distance over time. We can say that power is equal to force times velocity because velocity is equal to distance over time. So V is the velocity of the moving object. The SI unit of power is called the watt, which is the symbol for the watt is W in capital letter. 1 watt or the watt is defined as the rate of transfer of energy of 1 joule per second. So 1 watt is equal to 1 joule per second. We have other larger units of the watt, which are the kilowatt and the megawatt. So 1 kilowatt is 1000 watts and 1 megawatt is 1 million watts. Sometimes, like I said earlier, the horsepower is also used as the unit of power, and 1 horsepower is approximately equal to 746 watts, which is the same as 3 over 4 kilowatt or 0.75 kilowatt. And you should also know that the unit of buying electrical energy or using electrical energy is the kilowatt hour, kWh. This is the energy used by an appliance with the power of 1 kilowatt in 1 hour. 1 kilowatt hour is equal to 1000 watts times 3600 seconds, because you know that 1 kilowatt is 1000 watts and an hour is 60 by 60. That will give us 3600 seconds. So that will give us 3.6 times 10 raised to the power 6 joules or 3.6 megajoules. So it means that 1 kilowatt hour is equal to 3.6 megajoules. Thank you for watching this video. Please like our page, use science, and also subscribe. See you soon.